All right, today we're going to tackle a classic physics puzzle, one that really seems to defy logic at first glance. This is one of those questions that can trip up even experienced students, but its solution reveals something really profound about how we perceive motion. So get ready to see something wild, how a ball can have angular momentum without actually spinning at all. Okay, so let's just dive right in. I want you to picture a ball just dropping, straight down. There's no spin, no curve, just a simple, straight line path thanks to gravity. So how in the world could it possibly have something called angular momentum? I mean, the name itself implies rotation. It really seems like a paradox. But as you're about to see, the real secret isn't about the ball's motion. Nope, it's all about our point of view. Okay, so here's our game plan for cracking this thing. First up, we'll define the puzzle precisely. Then we'll grab our physics toolkit with the laws we need. After we set the scene with our coordinates, we'll get to the heart of it and calculate the hidden twist, or torque. From there, we'll find the final answer, and finally, wrap it all up with the key lessons this problem teaches us. All right, section 1. Let's get straight to it and lay out the exact problem we're trying to solve here. So this classic puzzle is from the famous Irodov collection, problem 1189. It asks for the change in a falling ball's angular momentum. But here's the absolute game changer. Our observation point, this point O, isn't stationary. It's moving horizontally. Seriously, this one little detail, that our perspective is moving, that's the key to the whole thing. Section 2. Now, this might sound a little intimidating, but trust me, we only need a couple of fundamental laws to crack this nut. So let's open up our physics toolkit. First up, angular momentum, which we denote with a big M. Now, don't just think of spinning tops. It's really a measure of an object's, well, its quantity of rotation about a point. The formula is a vector cross product. The position vector r from that point to the object crossed with the object's linear momentum p. So what does that mean? It means angular momentum depends on not just how the thing is moving, but also on where it is, relative to where we're watching from. Next in our toolkit is torque, big N. The easiest way to think about this, it's the rotational version of force. It's the twist that makes things rotate. And hey, look at that formula. It's another cross product. The position vector r crossed with the force vector f. This is so cool because it shows that a force, even a straight one, can create a turning effect if it's applied at a distance from a point. And right here, this is the master key. This connects everything together. The rate of change of angular momentum, so dm over dt, is exactly equal to the net external torque. This is basically Newton's second law, but for rotation. If you got a net torque on a system, its angular momentum has to be changing. This is the equation we're going to use to solve our puzzle. All right, section 3, setting the scene. I can't stress this enough. This next step is absolutely the most critical part. We have to define our vectors perfectly or nothing else will work. Okay, let's lay down our grid. The problem tells us the ball starts falling from point O. So at time equals 0, they're in the same spot, which we'll just call the origin. Simple enough. From there, the ball drops straight down, along the negative y-axis, but at the same time, our observation point O takes off to the side with a constant horizontal speed, v, along the x-axis. Okay, now here's where the magic really happens. Let's look at how we write our vectors. The force vector, F, that one's easy. It's just gravity, right? So it's pointing down in the negative j direction. No big deal. But the position vector, r, oh, this is the really clever part. Remember, it's the vector that points from our moving point O to the falling ball. Let's think about that. Horizontally, the ball just stays at x equals 0, while point O scoots over to x equals vt. So the relative x part is, well, it's 0 minus vt, which gives us negative vt in the I direction. Makes sense, right? And vertically, the ball's position is just your standard freefall equation, negative 1/2 gt squared in the j direction. This relative position vector, honestly, getting this right is the entire secret to the problem. Okay, we've got our tools, we've defined our vectors, now for the fun part, the calculation. This is where we finally uncovered the twist in the tail, literally. Okay, let's walk through this step by step. We're finding the torque using our formula, N equals R cross F. So we just plug in the expressions we just worked so hard to find. Now remember from vector math, the cross product of any vector with itself is 0. So that second term, the one with j cross j, poof, it just vanishes, gone. So what are we left with? We have negative vt, I, crossed with negative mg, j. Okay, first, the two negatives cancel out. And then, using the good old right-hand rule,
I cross j gives us k, which is a vector pointing straight out of the screen at you. And there it is, a non-zero torque. This is our aha moment. Can you see it? Even though the force of gravity is pulling straight down, because our viewpoint is moving, it creates a lever arm that produces a real, measurable torque.
We did it! We found the torque. So now it's time for the final push, the last phase of the calculation, where we use this result to get the total change in angular momentum. So let's go back to our master equation, right? The rate of change of m is n. To get the total change, we need to add up all those little bits of torque that are being applied over the entire fall. And in calculus, adding up little bits just means we integrate. So we're going to integrate our torque function with respect to time, all the way from the beginning, t equals 0, to the final time when it's fallen the full height. But wait, before we integrate, we need to know what our limits are. We need to know how long this ball is actually falling. So we just pull out our basic kinematics equation for free fall from height h. We can rearrange that to get an expression for the final time squared. And here's a little trick. We don't actually need the final time itself, just tf squared, which is simply 2h over g. Let's just tuck that away for a second. We'll need it for the final step. All right, now we can do the integral. The total change in angular momentum, which we call delta m, is just the integral of our torque. Now look at our torque expression. M, v, g, and the vector k. Those are all constants, so we can just pull them right outside the integral. We're left with the super simple integral of t with respect to t. And what's that? It's just 1/2 t squared. We evaluate that from 0 to our final time, tf, which gives us a nice result. 1/2 m v g times tf squared, all pointing in the k direction. And now for the grand finale. Remember that expression for tf squared we put aside? Let's substitute that into our result. And would you look at that? The 1/2 and the g from our integral cancel out perfectly with the 2 and the g from our time expression. It's so satisfying. We're left with this incredibly clean, simple, beautiful answer. The total change in angular momentum is just the mass times the velocity of our reference point times the height of the fall. And just like that, the paradox is solved. Whew, okay, so what did we just learn by breaking down this awesome problem? What are the big ideas we should take away from all this? First, and this is huge, angular momentum is fundamentally relative. You can't just talk about it in a vacuum. You always have to ask relative to what point? Because changing that point can completely change the answer. Second, a force can create a torque as long as its line of action doesn't go straight through your reference point. In our case, that moving origin created a lever arm for gravity that was constantly changing, and that's what produced the torque. And this brings us to the common pitfalls, the mistakes people always make. Number 1, forgetting that the position vector r has to be relative to the specified origin, not just some fixed point. And number 2, forgetting that torque and angular momentum are vectors. That direction, the k-hat, is just as important as the number. And this whole thing leaves us with a really big, kind of mind-bending thought. The entire puzzle, the very reason we found any angular momentum at all for a ball just falling in a straight line, it only existed because we chose a moving frame of reference. It just makes you wonder, doesn't it? Where else in physics, from Einstein's relativity all the way to the bizarre world of quantum mechanics, does a simple change in perspective, a different way of looking, completely change our understanding and reveal some hidden truth about how the universe actually works?